systems. Now, there are interesting things that happen when you have a field theory that has a gravity dual. So in that case, you have on the boundary, you can have your boundary, and you can have your region A as being some region on the boundary. That region A has a boundary of the region, right? That surface, that's the codimension 2 surface. Now, if you had an ordinary defect, you would have the defect sitting here. And in gravity configurations, that defect typically is related to a brane that is sitting in the bulk that ends on the boundary. And then computing the expectation value of the defect. So this is a general property of defects. It's usually some classical action of usually it's the area of the defect, okay? With some couplings in front that are related to the kind of tension that the defect has. So let me put tension times area. Okay? That's typically the formula you will get for defects. In some cases, it's a little more complicated because the defect is charged and it couples to the charge, the gauge fields, and so on in the bulk. Okay. Now, for entanglement entropy, you get that the entropy is equal to the area of a minimal surface that ends on this boundary divided by 4g Newton. Okay. So that's the what the dictionary is telling us. So here the computation of entanglement in the boundary theory translates into a geometric condition here in the bulk. Okay. So that's a connection between entanglement and geometry. So the pattern of entanglement of the quantum fields on the boundary theory is related to a geometrical property of the bulk, okay, which is the area of these minimal area surfaces. This formula was originally conjectured by Ruta Kayanagi, and then we argued, that was true. So. This is the leading statement. And this leading statement, well, passes, of course, all tests of entanglement entropy. Entanglement entropy obeys many inequalities. So the relative entropy one is one quite non-trivial one. And you can check that it passes those tests as it should. One can also talk about subleading corrections. There are two kinds of subleading corrections when we think about entropy. So one is your classical action in the bulk might not be Einstein, but might be Einstein plus some higher derivative corrections. And in those cases, you get corrections, again, that are local on the surface, that are somewhat similar to the Wald form. They're not exactly the same as the Wald form. But again, they are things you can derive once you know the action. So if you know the classical gravitational action, you can derive those corrections. This hasn't been done in general. It has been done only for R-squared terms. But well, hopefully it will be done in general. But that's one type of corrections to the entropy of black holes. And then,
what's the interpretation on the boundary?
Well, the interpretation on the boundary is just simply the only thing that has an interpretation on the boundary is the whole entropy. Okay. Now, I could say a little more about this. So, in string theory context, typically we have an action which is square root of GR plus some alpha prime corrections, right? Things like this. And so, in that string theory context, these higher derivative corrections can be viewed as higher derivative alpha prime corrections. But they are still leading order in 1 over g squared, right? So they are effects of order n squared, but that higher order in the 1 over square root of lambda expansion. So that's more detailed. Okay. However, there are also corrections that have to do with honest one-loop corrections, so terms which are g to the 0 in the bulk, or that are independent of the Newton constant in the bulk or these constants in the action. And those are given by the following. So you take, let me draw, just to make it more clear, this is a spatial direction on the boundary, and this is the bulk. So there is, let's say, some region A here. And this Rutakanai surface is a minimal area surface, extends into the bulk and reaches the boundary. As usual, has infinite area, the infinity is expected, blah, 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 has a finite interesting factor, etc. So that gives the leading order term the area of the surface. But now we have some bulk region, which I'm going to call AB. Okay. So this is the bulk region, which is inside the surface and connected to region A. Right. So the one-loop correction is the S entanglement of region AB. Okay, in the bulk. So this is, let me call bulk entanglement. So that's the non-trivial part of the one-loop correction. It's just simply the entanglement entropy between this and the exterior in the bulk. Okay.
You wrote alpha prime correction to the effective action. Can also, the one-loop correction, some of that can also be expressed.
Yeah, some of that. So the part that is expressed as in a local way, you include here essentially in the what we call the class.
So the entanglement entropy is on the top of that?
Yeah, on top of that. Yes. Yeah, you can separate them clearly. So, well, this you can separate them clearly because, and just to make, let me just describe one setup where it's separated very clearly. So let's go again to this. Let's imagine we are computing the entanglement entropy between regions. We have a region A here and this region A tilde here, right? So here we had these minimal area surfaces. And so if we calculate the mutual information between A and A tilde, right? So this mutual information is identically 0 for all walled corrections. And the reason is that all these walled corrections are given by a local integral on these lines, right? And the so recall that this was S of A plus minus S of A union A tilde, okay? And the minimal surface for A is this, and the important thing here is that the minimal surface for this is just the union of these two. So they precisely cancel to all orders. But the entanglement, the bulk entanglement entropy is doesn't cancel. So there is here some bulk entanglement between these two, and this doesn't cancel. So that's why I said that this is the non-trivial piece of the correction, of the one-loop correction.
The finite part, like to throw away all the, you regularize, remove all the divergent parts, and that's what you mean by this bulk entanglement?
Yes, yes. So this is, unfortunately, I will not go into the details. So there is a way to define this correction. I lied slightly here. Well, I didn't lie, actually. There was something I went over. I said this was the interesting part, right? There are more uninteresting parts, like all the divergences and finite terms which are local, which are given by local integrals on this surface. All those terms are qualitatively the same as the ones we had for higher derivative corrections. We don't care about them, okay? And they can be extracted. And there are some setups like this where this is the only contribution that gives you a non-zero answer.
Now, what would correspond if you did the analog of the I for the bulk use?
This is the I in the boundary theory.
No, I'm just saying if you did this I, since you're getting the bulk entropy.
No, let me just make the formula and then maybe you'll ask again. This is equal to the I of the bulk between A bulk, A tilde bulk. Okay.
Oh, it's already that.
Yeah, it is that. So the point is that the entropy of each region is given, it has a piece that is just the bulk entanglement entropy of the region. So when we do the mutual information, again, the bulk region for this piece is just the union of these two bulk regions, right?
Doesn't S of union of A and A tilde include some small correction, subleading correction, which has to do with minimal surface connecting A and A tilde? Contribution?
I've chosen this to separate it like this. I erased what was here and I separated them so that this question would not arise. In principle, there could be a correction that there could be situations where, I mean,
yeah.
You could also have this guy,
Yeah.
right? And yeah, this is a correction, but it's a subleading correction. It's exponentially suppressed compared to the pieces we are.
Nonetheless, it's a correction.
It is a correction.
And it's neither kind of.
Well, it's like e to the minus n correction. So we are doing an expansion in powers of. So this is of order, let's say, n squared. This is of order 1. Okay. And what you're talking about is e to the minus n squared correction.
And is there new divergence associated with it?
No. The divergences are all local here, and there are no new divergences. Yeah. So.
Is there some worldsheet prescriptions so that you could compute?
Yeah, that's a very good question. Well, yeah, I keep asking these questions to everyone who's interested in entropy in string theory. So there is a formula for black hole entropy in gravity, which is the area. There's the Wald formula, and the Wald formula should be an approximation to something in string theory which should be valid for finite alpha prime, which is I think what you're asking about. So at classical order in string theory, if you are given a sigma model that has a target space which contains a horizon, then there should be a black hole entropy formula, which is something you can calculate in this black hole sigma model. I think it would be fun to know what it is. And then you take that, and if you were to expand it, you would rederive Wald's formula. Yeah. Now notice there is something different between superficially this prescription for the Ruta-Kanai prescription for the entropy looks rather similar to what you would do for a defect. Okay, for a defect that has a tension, has this huge tension. But it's actually different because for a defect you have an actual brain that is sitting here in the interior. Okay, and if you wanted to calculate the quantum fluctuations, you would do the quantum fluctuations of this brain. Right, there will be some fields, and you would do the quantum mechanics of these brains, and so on. While here, what we have is an imaginary surface. Right, there is nothing there. There is just an imaginary surface in the bulk of space-time. I think that's what makes this formula quite distinct from other formulas for defects. And, well, it also has to obey all these various inequalities.
But perhaps the related question might be, how do you bring out an entanglement entropy in a physical computation if you want to experiment with? Good.
Yeah, that's also a good question, for which, of course, you are not going to be able to do. You're not going to be able to do the von Neumann or Dirac measurement because it's not linear in the density matrix. So in an actual experiment, you would have to make the actual copy. So the proposals to measure it involve making actual copies of the, right, and coupling them and so on.
By the way, a related question. So in mutual information, though, as you said, it's balanced from above of this correlation between systems, A and A tilde.
Yes.
So presumably one can sort of at least estimate entropy, mutual information from below by looking at various observables in one.
Exactly, yes, that's right. Yeah. Right. Now, this question Kumram was asking about how you measure. So it seems difficult to measure, and it's not linear in the density matrix. So one is tempted to throw this is a bad notion. Entropy is a bad notion. But I mentioned many things that were useful about entropy, like proving the C theorem or finding a C function. There are many non-trivial things you can argue using entropy. And well, of course, we use it in thermodynamics. So before you throw it away, you should maybe think that there is something useful. Okay. There is. Well, let's see. Well, so now let me. So this Ruta-Kanai formula is telling us that somehow the entanglement entropy, is computed by this minimal area formula, and therefore this surface has something to do with the pattern of entanglement. It has something to do with how the degrees of freedom are organized and how the bulk emerges, and that can be actually made a little more qualitatively. I mean, there is a nice qualitative picture in terms of something called tensor networks, but I probably will not discuss it in detail. I will just jump to the most extreme version of this story. Well, if someone wants to ask, I can do that. So the most extreme version of this is to consider two field theories which are actually disconnected. And so we can have situations where we have two boundaries. So we have a field theory 1, and then another field theory 2, right? Each living on its own space, completely decoupled from each other, but they could be in an entangled state. In the same way that we can have two spins that are very far away, decoupled from each other, and they can be in an entangled state. We can consider two field theories which are in an entangled state. And for some situations, that field theory, that the geometry that describes that state, is such that there is a geometric connection between the two field theories. So the simplest example of this is one that you get from thinking about the thermal field theory, and it's the following. So imagine that you consider a field theory at finite temperature. Okay, so what I'm going to do now is to produce a particular entangled state. Okay, so this is just a way to produce an entangled state. So field theory at finite temperature is given by taking the time direction and making it a circle of period beta. Okay, and then if we evolve, so we can think that we take the field theory here, we evolve it, and we sum over all the states with the factor. Of course, this gives us just the free energy, right? Good. Now we can do something slightly different, which is to evolve from here to here, and then we get something that depends on two states. Okay. So we do the path. So we fix some boundary conditions here, we fix some other boundary conditions here, and then we do the path integral over Euclidean time, right? And then what we get is some state, which is sum over n of e to the minus beta En. So this is the energy of each state. And then we have here two field theories, one right field theory and one left field theory. They are completely decoupled, and we have a state on the right and a state on the left. If we do this properly, this is the CPT conjugate. But yes, there is a half in beta. So that's what we get because we evolved only over half of Euclidean time. And then this so if you get the state normalized in this way and you take the inner product with itself, you get the free energy. Anyway, so this is just a way to construct this state. If you wish, it's a mathematical way of constructing this state. But now let's look at the situation where we have a gravity dual. So if the theory has a gravity dual, then we had this circle on the boundary, and then there is the bulk, and in suitably high temperature phase, this circle shrinks smoothly in the bulk. Okay? So it's a contractible circle in the bulk. And so we can actually draw that as a circle. This is the boundary circle, and then the bulk is, so if you view it from this side, you have the boundary circle, and now the bulk is filled. So we come back to this, and this is, let's say, rho equal to 0, and this region here corresponds to rho equal to infinity. That's the boundary, right? Far from the point where the circle has shrunk to 0. And so now you can take this Euclidean geometry and cut it here at the Euclidean time. You can view this as some 0 for Euclidean time, and continue to Lorentzian signature. And you can do this both on the boundary theory, and in the boundary theory you simply get two separate boundary theories that start out at initially in this state, and then you evolve in, let's say, you can evolve in some t left and some t right, and Lorentzian times here. And so here we are doing that, and in the bulk, what we get is we get the 1/2 of the eternal black hole in ADS. So this is the the eternal black hole in ADS is a particular black hole. Well, this is the Penrose diagram of those black holes. We have, this is the boundary of ADS, this is the horizon, and it's maximally extended, so we have a second boundary, and so on. So these are black holes that have two exteriors, so this is exterior right and exterior left, and one interior. Well, of course, the future interior and this past interior. When you think about this, don't think of this as the interior. You're going to get confused if you think of this region as the interior. The interior is here. Okay. Okay. Now, so I did this in detail just to argue that this spacetime should be viewed as the geometric dual of a field theory computation that we do involving this state. Okay. So we have two completely decoupled field theories, and we have some state, some entangled state between these two field theories. Now, this thing was discussed by Israel some time ago, and it was usually viewed as, well, some trick that you can do in any field theory at finite temperature. You can always double the system, and it's some trick you can always do and consider now a pure system into copies of the field theory as a way to think about the thermal ensemble. But you can also view this as you can view this geometry as actually the geometric dual of this entangled system. So you have this. I think this is a quite dramatic statement that we have a geometric connection. So if you look at this surface, for example, it's a surface that connects the two field theories. So the field theories are connected through the bulk, even though they are not. There is no term in the Hamiltonian that connects them. They're just connected by the fact that this entangled state is the same two field theories could be in other states. They could be in the vacuum times the vacuum, right? And in that case, we would have two separate copies, and then the ADS will just end here, and there are two geometries completely disconnected.
So there are some class of entanglement state that has realization in terms of smooth geometry, or how generic?
Right. Yeah. So how generic is this statement? Well, it's enough to have one example to show you that geometry doesn't depend on the boundary Lagrangian and so on, but it depends on the actual state, and that you can have these geometric connections, and you can have the topology of space depends on the state your theory is in, and so on. Now, you can do small variations of this. So you can, for example, instead of producing this, so the simplest variation you could think of, so would be to add a local operator here, for example, in this evolution. So this will produce some particle, and well, then this will give you this black hole with some particle living in the black hole geometry. You could introduce any number of operators, and you'll get more complicated particles, right? Now,
but if I come up with some random,
good. Okay, yeah.
When do I know there is a geometric connection?
Right. Well, I think we don't know. There is no.
Even a more basic question: you can conflict the two different gravity systems, so that there will be no buffers connect them, presumably, right?
No. So well, no. That there are some cases where they connect them. So, okay, let me give you an example of that in a second. We don't know the general answer to your question. We know cases where it cannot be connected by a smooth black hole, but well, this is similar to the question of which field theories have gravity duals, right? So have gravity duals with a smooth geometry. So I would call the cases where this geometry is not smooth, well, analogous to those cases of field theories.
Supposing that I have a theory whose vacuum and correlation function on that is known to have gravity dual.
Right, right.
So take some
Yes, yes.
entangled
Good,
state
good, good, good.
within that theory.
Yes, yes.
Are there criteria where?
No, I don't know of a criteria. So there have been so this geometry is very special. It's very special because there is this point where essentially the two horizons are very close to each other. Right? There's this point in time where the two horizons are really next to each other. So for example, if you had a quantum field here and a quantum field here, the two-point function of these quantum fields would be pretty large. And take the same field and consider its boundary correlation functions, it would be pretty large. It would be of order 1 at this time. If you do the same at later times, it would start decreasing. Okay. Now, one can argue that if you had a generic, so Maroff-Alponshinsky argued that if you have a generic entangled state, the correlation function for any two operators at any time would you can find in generic entangled states would be typically always small, always of order the entropy. Okay. So what that is saying is you could interpret this in two ways. So one, which is the way they prefer, which is saying that these wormholes cannot have an entangled, some smooth geometry. Or you could simply say that the wormhole is longer. So these two horizons don't need to be touching each other. I'll just mention in a second one example where they're not touching. And there doesn't need to be a point where they actually touch each other. Okay. So, for example, you can take exactly the same state that we discussed here, and then you can. So one thing you can do is you can deform it by making some unitary transformation here that sends some particles that into the horizon. If you do it early enough, then these particles will arrive with high energy there, and then the black hole geometry will look more like this. Okay, so by sending some particles here, we've separated a bit this point. They are still null separated along this direction, and that we can again by doing a unitary transformation here that sends some particles in the in the early past. You can have a situation where it looks more like this, where the two horizons are really separated from each other, right? So these are just some examples of how you can separate the two horizons. There are other examples which are related to the question that Kumrum asked. So you can have a situation where it's not quite two different field theories, but it's the same field theory, but at different values of the coupling, for example. But it's an example where you go away from two identical systems. So in that case, you can put, for example, here one of these Janus walls that change from some value of the coupling G1 to some other value of the coupling G2. And people computed solutions to, first in the Euclidean regime, and then analytically continued to Lorentzian regime. And the Lorentzian version of those computations, they basically look like this. So they are situations where, again, the two horizons are separated from each other. The minimal area surface, so if you calculate the area that has the surface that has minimal area, it's actually here in the middle. So that's the one that is supposed to compute the entanglement. And these horizons presumably compute only the coarse-grained entropy of the system. And from the point of view of the outside here, it looks like a solution that is time-dependent. So there is some the scalar associated to G, so it comes out of the horizon and then goes back in. And then the coupling G, moving from here to here, moves smoothly between the two. So that's an example of two different systems. Now, if you ask, well, how could it be for two completely independent systems? So let's say we have a black hole. One of these n equal to 4 supreme. Well, let's say a system with a gravity dual on one side and a bunch of spins on the other side. So what could it look like? Well, certainly on the side of the spins, we don't expect any geometric construction.
I think my question was more like, for example, you have ADS, for example, 7 times S4 and ADS 5 times S5. And since your quantities are different, even you didn't have the same space, even right, different dimensions.
Right.
You could have gravity.
Right.
You could try to do the same entanglement, but that.
Yeah. So in some cases it might be. I think probably the most of them will not be very geometric. That's what I would guess. But I think here the point is not so much that which have a smooth geometry described by Einstein's equations, but in quantum gravity we're trying to find quantum generalizations of Einstein's equations and so on. And those would be, I don't know, some quantum generalization. But the quantum this should be viewed as a constraint on the quantum generalization of Einstein's equation. It should be such that it should allow for these things to happen. It should allow for geometric connections to come out of just simply pure entanglement. Let me yeah. So imagine you had a pair of black holes. Let's say you have some black hole here, black hole right, left, and some black hole right, very far away, right? So they are separated by a very long distance. Let's say one is in this galaxy, the other one is in the Andromeda galaxy. But through the horizon, they could be. So if they are described by, you can take the eternal black hole geometry, right? I'm now discussing Schwarzschild. So which is this, which in principle these two asymptotic spaces are different, but you can write down a solution which is essentially the same, but where the two spaces are actually the two sides are. Should express this more clearly. This is a solution where the two asymptotic regions are different. So let me just draw this slice. So on this slice we have this geometric connection between the two. At this point, the area of the transverse two sphere is finite. So that's this region here. And that's the shape of that spatial surface. And then we can evolve it using Einstein's equation, solution of the constraint equations. Now we can imagine a different setup where the initial surface is given by the same, we cut it here, and then we put these two regions in the same surface. And then we view this as some initial conditions, and then we evolve future in time. And it will not give us exactly the same geometry. It's a small 1/r potential between the two. But if they are far away, they will give us essentially the same geometry. Okay. That's just to argue that that this is we could consider the two black holes in the same space-time. Good. Now, if you had such a situation, then we think that that space-time should be viewed as an entangled state of two black holes, where here we are summing over of this form, where here we are summing over all the microstates of these black holes. Now, what happens when? Okay, so then in this situation we say that this surface that I just drew, that I unfortunately erased, sometimes called the ER bridge, okay, the Einstein-Rosen bridge that connects the two regions. This surface was, so they thought about the surface even before realizing that the space was smooth. But anyway, and so in this case, this surface is coming out of the EPR entanglements. So we can say that ER is equal to EPR in this situation. That the Einstein-Rosen bridge arises from the EPR state of two black holes. And this shares some properties with this configuration of two black holes shares some properties with EPR correlations, in the sense that we cannot send a signal using this bridge. So if we look at the black hole geometry, and we are sitting here, and we want to send a signal to someone who's sitting here outside the black hole, we cannot, right? So any signal will go into a singularity and will not reach the other observer. Okay?
Could I get a clarification on
Yes.
that? So left to the imply right.
It's mostly that ER is one particular case of EPR.
Mm-hmm. So it is in that sense.
Yes. Yes.
Inclusion.
Yeah, an inclusion. Yeah, if you wish. But you can say that quantum gravity should be the quantum version of ER should be somehow EPR. But well, that is just vague. I mean, but I think it's interesting to think about what this implies for the interior. So there is this interior vision, and so notice that this person cannot send the signal to this guy, but if this person jumps in, right, he can receive a signal from this guy, right? So if I'm trying to, so even though we cannot communicate with the other guy, if we both jump into the black hole, we can certainly communicate. Or if I jump into the black hole, the other guy can send me signals, right? So I think this shows quite clearly that the interior of the black hole does not depend purely on the black hole microstates. Okay, so this is an important point. Because what you will experience on the interior depends on what signals this other person. Yeah. No, this guy was jumping. So when you jump into the interior, what you experience will depend on what signals this guy decides to send you. Okay. So this is certainly true for black holes that are highly entangled. It's certainly true for black holes that are entangled in this particular state. And
but in this description, it's the black hole entropy. Entanglement.
Yes, yeah, I guess it.
Sure what you refer to as black hole entropy and microstate as having separate realization.
Yeah. So
this sentence seems to suggest that the
okay.
Yes. The notion of black hole.
Yeah.
Could you clarify?
Yeah. So we have a black hole sitting at some point in space. We normally think that there is a certain number of black hole microstates that is given by the black hole entropy, right? Given by the area formula. And this counts the number of states this black hole can be in as seen from the outside. At least certainly seen from the outside, right? And we think of these states as somehow living in this region of space-time. At least from the outside, they are somehow localized in this region, right? And naively, you might have thought that if you fall into this black hole, what you experience only depends on these microstates. That somehow the interior comes out of, some effective dynamics of these microstates, right? If that were true, then when we entangle these microstates with these other microstates, we shouldn't, naively would say we shouldn't care, right? This is in some thermal, these microstates are in some thermal system, and what I experience, naively would say I should not care of.
Well, if you entangle those, in some sense you have traced over the black hole microstate, and
yes. So here
you use the entanglement in place of that.
Yeah. So here we have. So from the point of view of this side, we have a thermal system, a thermal black hole. So we have we don't know what microstate the black hole is in. We have a thermal. It's the same as having a thermal quantum system. It's like having a thermal spin with a density matrix described by the thermal one. And then you can ask, well, what happens if I fall into this black hole, right? So is my fate determined simply by thermodynamics? Is the interior just some way of doing the thermal averages of what will happen to me, or does it depend at all on what other system my black hole is entangled with? And I think this example shows that at least for this particular entangled state, what you feel when you fall into this black hole depends on what signals the other person sends you, right? So.
So I'm just raising the question of when you say when you write only on black hole microstate.
Yeah.
well, it sounds like it's a separate notion in addition to the entanglement.
Well, let me see. So black hole microstates, we agree more or less what we mean, right? Is the thing that...
Exactly. So yeah, I'm not sure I understand
what? No? Yeah.
So
black hole? So black hole microstates are some states in the Hilbert space, which an observer here, far away from the black hole, describes as defines all of quantum gravity in terms of some Hilbert space, right? And
Hilbert space, which is sort of attached to the region.
Yeah, it's attached to some region around the black hole. So we go some long enough region, we have this Hilbert space. We count states in this Hilbert space with this energy, and we get the black hole entropy, and those are the microstates we are talking about.
In that picture, wouldn't that include also the right region? I did this on the right region. Would it also include all the stuff which is happening on the left region?
No. So it would involve the states of this black hole. And well, here there is a separate, yeah. So bulk locality also implies that these two Hilbert spaces, I'm also making the assumption these two Hilbert spaces are separate. We have two separate Hilbert spaces. One that is describing this black hole from the outside, one other one that is describing this black hole from the outside.
It actually fails in the example, right? So it's not actually true that there is locality in that sense. That the Hilbert space attached to black hole 1 is actually not independent.
Well, that's you could say that. I would say that the two Hilbert spaces are independent, but there is they are entangled in some particular state. They are in a particular entangled state.
If you imagine forming a black hole by collapsing matter,
yeah,
can you?
No, you can
figure something to make an ER bridge.
Yeah. So the ER bridge is very, very special. It's a very special state of two black holes, and it's very difficult to make in the sense that if you make small perturbations here in the past, you will destroy it. Okay.
So what's the argument?
Let me.
It's actually physical. Is it?
Yeah.
For a Schwarzschild black hole.
Yeah. Well, no, for Schwarzschild black hole. I mean, if you have a Schwarzschild black hole in our universe, it's certainly not physical. It will not be joined with ER bridge to some other, so with this ER bridge to some other.
How am I supposed to think about that?
Yeah, so an actual black hole, this is a special state of two black holes. You can ask the question of whether I could, in principle, make this very special state. The generic state for a black hole is that you will, if there is something like this, so you can have a generic state of a black hole is you could collapse the black hole, right, and it will be in some microstate. It's not entangled with anything else, right, and so there is no bridge or anything like that. And indeed, for a black hole that has just collapsed, I'm ignoring the effects of black hole evaporation in this discussion right now. So you collapse, and this is the Penrose diagram, and there is no second copy. It's not entangled with anything else. So that's the state in which black holes that form in our universe will be in. So now, yeah.
Imagine if you had some macroscopic entangled things collapsing.
Yeah, so if you had, yeah, well, let me give you one example where you produce a state which is very close to this one. So if you had a constant magnetic field, let's say, right, then you could, in principle, pair produce magnetically charged black holes, right? Let's think first of the black hole as a particle. So the instanton that describes the pair creation is a circle in Euclidean time, right? When we cut to go to Lorentzian time, we get the circle, and then so we have a positively charged, magnetically charged black hole and a negative one that they will accelerate in the magnetic field. Okay. Now, when you actually look at what these geometries look like, so we have the circle is the trajectory of the charged black hole, but you look very close to here, and the geometry is locally, it's let's say near extremal black hole. So it's S2 times AdS2, and this AdS2 geometry really looks like a disk, which ends on the circle, but is connected here, right? So this circle shrinks in the AdS2 region, but that's a different shrinking than the original shrinking circle that we had here, right? And in fact, the distance here is longer, not by very much, but not. So this distance is logarithmically shorter than this one. So this distance is some distance scale L, which has to do with the size of the magnetic field, and this distance is of the order of log L. So in that sense, it's smaller. So this is a situation where you again produce an ER-type bridge. Now for the magnetically charged black hole, so the full diagram looks more complicated. So it's something like this. Anyway, so it's this surface here in the extended Penrose diagram of the charged black hole now. So this gives you a way to produce them. It's of course a tunneling process, so it's exponentially suppressed. So it's very improbable to produce them in the first place. The tunneling rate is of the order of e to the minus some constant times the black hole entropy. Right? Well, this formula is a little misleading. I should say the production rate is very small. Let me just say it this way. So it's a very artificial situation. So this, I don't want to say that this particular black hole is the generic state in which two black holes will be in. No, I'm not saying that. This is a very, very special state, but the general theory about black holes should take into account this special state, number one. And number two, if you have a black hole which is maximally entangled with something else, maybe it might look something similar. So it might be in the sense that what happens to an observer here when he falls in might depend on what signals are received from the other side. So if the correct picture, let's say, instead of being what I said, so for the black hole, so here was the black hole. Let's now imagine that it's maximally entangled with Hawking radiation. Let's say we have all the particles of Hawking radiation, or we transfer Hawking radiation to a bunch of spins. What could the connection be? Well, there is some kind of connection between this, right, which is the entanglement. These dotted lines are not more than entanglement. How is this entanglement going to be manifest in this geometry? Well, in this geometry, we had something that was coming from the left, okay, into the interior region. So there are two extreme alternative scenarios, I would say, for how that the geometry looks like. One is the so-called firewall scenario, where if I look at I'm going to only look at this horizon here in the future. I'm not going to draw exactly what happens in the past, how we got here. So there it says that there is some singularity here. So this is the firewall scenario. So they would say, yeah, indeed, what you feel when you fall into a black hole depends on the external system, and you feel that dependence right when you fall into the horizon. Okay, so you are destroyed here, and that's it. And the way you are destroyed will depend on the details of what state you are entangled with. Or some other possibility could be that, well, there is something you don't know very well here in the past, but that for most states it will look similar to the state of an ordinary black hole. So that for most states you can be entangled with, and for most entangled states there will be some difference, but that difference will be in the far past. And in most cases you can fall in without feeling anything strange. But you could certainly do something strange to the system outside in order to make you feel something, right? In the same way that this person could send you signals. So let's say if you have empty space, this guy falls in and feels nothing special, right? But here you can have some evil person that shoots you, and you will die before you reach the singularity, right? So what you feel when you fall through this horizon depends on the intentions of this evildoer here. And similarly, when you have, so it could be that when you have a black hole, again, entangled with radiation, so if you do something strange with the radiation, you can send in some signal or some bullet that will kill this person, but that would have to be something special. So, yeah. Now it's been this is related to well, I'm probably how much over time can I go? This is related to the firewall paradoxes. So maybe I'll discuss the original firewall paradox. I'll state it for those of you who have not may not have heard it. And
discussion we had earlier, with the discussion we had. So earlier you were pointing out that, well, you are agreeing that the generic entanglement would not be described by smooth geometry.
yes, let me answer this question a little bit. Yes. Yeah, so indeed.
It's not relevant to this discussion.
No, well, there is a question of, yeah, it's not relevant because so the generic entanglement, right? Already this system is not described by smooth geometry. This, I mean, state of many spins, right? But the question is where the transition between the non-smooth part of the geometry and the smooth part of the geometry occurs. So that's the whole discussion. Maybe I should say it this way. So the whole discussion is where the transition between the non-smooth part of the geometry and the smooth part of the geometry occurs.
Mm-hmm.
Does it occur right at this horizon, or does it occur somewhere else? Mm-hmm. So that's, I think, the question that is being discussed. And well, some people argue in favor of one or the other, and I think there is a consensus. Yeah.
Can one set up a geometry with a asymmetric ER bridge where the black holes have different masses? And then you could imagine one side evaporates first, and that could give you this kind of a thing in purely, without invoking spins or anything.
Yeah, I mean, already, yeah. I mean, if you, well, yeah, so in principle, the thing is anything, so if you start from some ER bridge, well, yeah. There are some solutions, for example, in 2+1 gravity, where you can have lots of little black holes entangled with some bigger black hole. There are some, this was considered first by a Swedish group that they consider all these geometries as quotients of, so you can have a situation like this and then try to continue this, and as more or less analogous to what we were discussing. So that's, I guess, one example. But all of these are very special examples. Anything that you can construct explicitly in gravity will be a special example.
Sure.
I think most of the discussion now is to try to understand what the generic situation looks like, and whether we can discuss clearly between the generic and non-generic examples.
So the question is that is the generic entanglement benign or non-benign?
Right. Where does the transition happen between the smooth geometry and the non-smooth geometry? Does it happen? So I mean, if you take the intuition from these ones and you make all these black holes very tiny, right? Okay, so you will have, you expect to have an ER bridge which, you know, on one side it will be fairly geometrical, and on the other side it will be kind of messy, right? But well, that messiness is probably going to be. I mean, when this is a situation with time reflection symmetry, so when we evolve into the future, that messiness will be confined to this side of the diagram. That's what you expect in those situations. But again, we did something special because we chose this to be something with time reflection symmetry that we could easily continue. I don't think there is a simple argument. Yeah, I don't know of a simple argument that would argue that this happens. We just said this might happen. So this is a possibility that is in agreement with what you expect from general relativity. So from general relativity to say that you will get a firewall at the horizon looks strange. Yeah, let me say, this is inconsistent. So let me see. This is inconsistent with GR effective field theory, general covariant effective field theory, which contains one postulate which is always been somewhat suspect. Let me call it adiabatic vacuum. So the postulate of the adiabatic vacuum says that whenever you have an expanding universe, all modes, new modes that come in below the cutoff come in the vacuum. Okay, so that's this postulate of the adiabatic vacuum, and that this vacuum is determined by the Lagrangian, the effective Lagrangian of your field theory. So if you change, any change in the vacuum is correlated with a change in the effective Lagrangian. So that's, I would call those the standard postulates of effective quantum field theory in curved spacetimes, especially as for expanding universes, both in inflation and in this black hole problem. So this is inconsistent with this. I mean, it could be that, well, there is some funny effect that we haven't understood that changes the story of the adiabatic vacuum. Why it happens in the black hole horizons, well, that hasn't been explained. So now, maybe, well, let me see, what could I discuss? I could discuss the firewall. I could shut up and not discuss it. Or I could discuss some of these firewall paradoxes.
Maybe some brief discussion.
Brief discussion, yeah. So there are 4 firewall paradoxes. Yeah. Yeah, with half an hour each, I think we are good.
This is our first question.
So let me. There is not one firewall, but there are many. And firewall is a solution to the paradoxes. So unfortunately, the name of all these things is all wrong. I mean, for everything. So there's a bunch of paradoxes, and there is a proposed resolution, which is the firewall. And there are other proposed resolutions, which are non-firewalls. And there are criticisms of all the solutions. So it's a messy subject. So most of it in the swampland, probably. But there will be one that will be correct. One, well, not one of the known ones, but there will be a correct answer. So first, firewall paradox. So here, what you say is you imagine an old black hole. An old black hole is a black hole that has existed for a long time and evaporated for a very long time in such a way that it's maximally entangled with its outgoing radiation. So the idea is that you form your black hole. Your initial black hole might have been in a special state, but then it emits radiation for a long time. And then the entropy in the radiation grows and grows and grows according to... And at some point, it becomes bigger than the entropy of the remaining black hole, right? So you would say that if that system is in a generic state, it will be maximally entangled, okay? Yeah, so it's the black hole plus the radiation. And so, let's draw it this way. So you have all the early Hawking radiation modes, right? This is going to be the early. Now we focus on a mode that will be emitted late. So this is sometimes called B mode. Now this guy will be emitted late and will join the rest of radiation, right? And if I were to collect all of the radiation, it would be in a pure state. Okay. Okay. Now, but this B mode is maximally entangled with this A mode inside, some mode inside the black hole. And in order to have a smooth solution here, I'm imagining a mode with frequency of order the temperature. Okay. So there is a pretty large entanglement with the mode inside. So we have this entanglement between these different modes. And now, if this is in a pure state, this guy should be maximally entangled with early. So we have 3 modes we're discussing. B, there is the early radiation, and there is the A, right? So this mode B has to be maximally entangled with the E and maximally entangled with A, okay?
When you say pure, you are ignoring black hole microscope?
No, I'm not ignoring. I mean, pure is after the whole black hole evaporated. There is no more black hole. After the black hole completely evaporates, if I include B and all the rest of the modes, that should be in a pure state. Yeah, I've unfortunately oversimplified this a little bit, so maybe. I take the full late radiation Hilbert space, right? Which are all the modes that reach infinity at different times. So this is at t equal to 0 and at t of evaporation. Okay.
What does A mean after black hole evaporates?
It means nothing. So it means nothing. So, but let me first do a preliminary thing so that we. So we have all these Hawking radiation modes that arrive at all these times. I select the ones that arrive early. Okay. But this is late into the game, right? So there are many more of this than there are of the later ones. So B is the first guy that will arrive after this arbitrary cutoff that I put.
Mm-hmm.
Now, the quantum state of all these guys, if I think, let me think of this as a kind of spin system. So they live in some Hilbert space of H late. And the whole thing lives in some kind of product of Hilbert space of the early and the late. And the black hole started its life, we are imagining the black hole started its life in a pure state. So we formed it from collapse of something simple. And so there should be, this whole thing should be in a pure state, right?
Assuming there is no remnant.
Assuming there is no, we are assuming there is no remnant. So this is in a pure state. And then we also assume the black hole dynamics is fairly generic. Some of these are not quite necessary, but they are useful for simplifying. So I'm assuming the black hole dynamics is generic, so that this is a generic pure state in this product Hilbert space. So it turns out that a generic pure state, if we trace out this guy, if we trace out the early guy, and we look at the density matrix here, it's close to the identity matrix, right? So in a finite system where if I were to trace out, I take a random pure state and I trace out these early modes, I'm going to be in close to the identity matrix. Okay. So that means that so when a density matrix is equal to the identity matrix, it means that the full pure state can be written as a complete, in terms of a complete basis of these guys times of these are the late modes, and this is some other state I in the early modes. This is some state which is the state that is correlated to this, and all these states are orthogonal. So this is a basis. We've chosen them to be orthogonal. And if we want maximal entanglement, all these guys have to be orthogonal to each other.
And the sum over I.
Sum over I, yeah, and the usual, I guess 1 over n or 1 over square root of n. Okay, so that's the, well, let me ignore this. Okay, so in particular, this basis contains a basis of the various modes, B1, B, etc. Right? So in particular, the mode B1 is entangled with something, right? It will be entangled with some other. Imagine diagonalizing all this in terms of a spin basis, and here we have a corresponding basis. And so this first spin is entangled with some state of the early radiation. That state will be a very, well, it's very complex combination of all the radiation modes that were emitted. Okay. So, but what is important is that this guy is maximally entangled with the rest. Nothing more than that is important. So that, okay. Well, I guess to make let make even simpler. So let's imagine we select here the particular of all these states. We select the two states that the qubit that is maximally entangled with this qubit B1. So then this is just a single qubit of the emitted radiation, and we're imagining of this as separate qubits. So instead of modes, let's imagine they are qubits. Now there is an entropy inequality that says that one qubit cannot be maximally entangled with two other systems. So so this situation is impossible. So either one of these two entanglements shouldn't be there, or there should be a mistake in this discussion somewhere else. Okay. Good. Now, maybe one way you could say this is, well, who cares? I mean, this is a very complicated setup, and let's. Yeah.
You said B and E is only a pure state when the black hole is fully evaporated.
No, not fully. No, not fully. It should be late. Yeah. So I used the fully just to explain why it should be maximally entangled, but then I threw away all these bits because they were in the. We are not looking at them anyway, and so we are looking only at this guy. So I've used the full evaporation to argue for this structure of the Hilbert space and argue that there will be this maximal entanglement. But now I'm ignoring all these qubits that will be emitted later and focusing purely on this time, right? One important point of this paradox is that we didn't use gravity to compute what this is. We used whatever correct theory of the black hole we had to compute this, or we think there is some way to compute it. We don't know what computes it and so on. There is no assumption that we use Hawking's calculation all the time, right? There is only the assumption that, well, we have this this pure generic state in this big Hilbert space. Okay. Good. So that's one assumption, and we reached this contradiction. So that's the first firewall paradox. So they proposed a resolution where A would not be entangled with B, and then that would be felt as something bad happening to the observer. If that happens for all modes, then an observer who falls in would see would feel badly at the horizon. Okay, so that's one, and then there are sort of the other ones that. So this story of ER equal to EPR was one way of trying to address the first paradox, and there are other people who suggested similar things, like Raju and Papadodimas and Berlindes, which is the idea that this mode A is actually not independent of the early radiation, that in some sense they are the same modes. So that, like in the, right, so that when we do some measurement here, we can, yeah, let me. In order to phrase the paradox a little more clearly, in order to make it more physical, what we could imagine is that we have a quantum computer that acts on the early radiation, right, and gives us a qubit E, which is maximally entangled with B, right? And then there is some observer that falls in and carries the qubit E that it was produced from the quantum computer, and then checks whether it's entangled with B, and then checks whether A and B are entangled. So such an observer that falls in could do that, right? So that's an operational problem that, and that observer would be surprised, I guess, if we had this entanglement between three. He would think that this quantum mechanics doesn't work. But what would happen is that since these early modes are secretly also produced in the interior, when you do this quantum computation of extracting the E mode, you are effectively sending a signal. In the same way that when we had the eternal black hole, if you do something on this side, you could be sending a signal that an observer that falls in will feel, right? And so yeah, so that's the idea, that you use this early radiation to construct the interior, and if you do something weird with the early radiation, then you will feel it when you go in. Now, in these discussions, it seems to be important to distinguish between complex operations on the early radiation and simple operations. So simple operations would be like measuring one of these modes and so on. And this operation that would distill the qubit that is entangled with B is a very complex operation. And so it was, so as a way to avoid the paradox, another possible idea is that you have some constraints on the time it would take you to do computations, and so that you, if you are talking about something too complicated, you are never going to be able to see a problem. So that's what sort of Harlow and Hayden argued. So they proposed some limits on how fast you could do this computation. They argued that it would take you a time of order e to the black hole entropy roughly to. So this is a huge time. So that is exponentially large, and then you wouldn't run into a contradiction. But so many of the ideas that are being proposed to resolve this paradox involve, well, this is one example, but there are other ideas also that involve complexity in some way, that complexity is important to construct locality, so that things that are close in space are things that are relatively simple to access, parts of the Hilbert space that are relatively simple to access. Things that are further away could be more complex operations in the boundary theory, in the Hilbert space. Okay, maybe I'll finish here and